Welcome to the introductory video about waves. The reading in this is really chapter 16, and you have sections 0 through 8, and then section 11, which relates to mathematics of how you describe a wave. Last time we looked at simple harmonic motion, and it's simple harmonic motion that creates a wave. That oscillation, that disturbance will create a wave, and it depends upon the orientation of that disturbance to the direction of travel of the wave that determines what type it is. Here's a real short segment describing longitudinal and transverse waves and the differences between them.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
So we're back. There's actually a third type of wave, which is called a surface wave. And it is really, it is a third type, but it's not really, because it's a combination of longitudinal and transverse waves together. So like if you were out in the deep ocean, your ship would be moving up and down because of a transverse wave. The tide would be considered a longitudinal wave. And where the wind brought these two together, you'd get a circular wave, which is called a surface wave. We'll look more at that in the next section. For examples, the longitudinal waves that we'll mainly look at is sound, and transverse we'll look at things like waves in a string, but also we'll look at light, which is two transverse waves together, and that is coming up. There is a lot of video here, vocab here, as you see. Amplitude, wavelength, period, and frequency. The amplitude I think we've already covered. I think you probably have a pretty good grasp of that. It is that maximum displacement. The wavelength is the length that the wave repeats itself in. It is a linear length measurement, so it's from one peak to one peak, or one identical part to another identical part. Where some people get very confused is, say they take the point where the wave crosses equilibrium, and that point repeats itself within a wavelength, it crossing that point, but when it first goes across that point, it is maybe moving downwards, and the next time upwards, and the third time downwards. So it's from identical points, which would be where it crosses the axis, both moving downwards. Lambda is our symbol here, as you see. For frequency and period, we had talked about those with simple harmonic motion. As you create, the period is the time for one oscillation, while the frequency is how frequently it happens, and they have that inverse relationship. What I want to spend some more time on really is talking about wave speed. Wave speed is not misunderstood, but attributed to the wrong factors a lot of times. And I really want you to put it into your memory banks that wave speed depends upon what the wave is in. We give that substance, that stuff that the wave is traveling in, a special name. It's called the medium. So the speed of a wave is based solely on the medium that it travels in. So here I've got a little simulation from PHET, and I've got a string here made up of particles, and if I set this to oscillate, you can see that it makes a wave. That oscillation, that simple harmonic motion of this green blob at the end, caused by the circular motion of this disk, remember that link, causes this wave. Now I can change the frequency. I'm going to hit restart there because it gets a little buggy on your eyes, and you can see it happens more frequently. Let's go way down on it. Let's give it a frequency down here, 10. I'm going to hit restart. Now what I want you to notice is how fast, say, a peak of the wave moves down the string. You can see a set length there. If I increase this frequency, I'm going to pause it. Oops. Come on. Pause it. I'm going to double my frequency. I'm going to hit reset. Do you notice what happened? Doubled the frequency, the wavelength, the distance from one part to an identical part got less. Right in here, let's change this back to 10 and hit play again. And maybe we can get both on the screen at once. Boom. So here's a wavelength for when it's 10. And here's a wavelength for when it is 20. The wavelength for 10 is twice as long as the wavelength for 20, because they control each other. They have an inverse relationship to each other. Here's the next thing I wanted to show you, though. I'm going to hit restart here. We've got our frequency of 10. If you notice, the wave speed didn't change when we changed the frequency. That's important. But if I change the medium, i.e. I change the tension in here, if I increase the tension, you should right away notice that the speed of the wave increased, even the ones that were already in it. If I decrease the tension, the wave speed, the speed that the wave moves along the string is slower. It's still oscillating at the same rate, but it's moving down the string is slower because the speed of the wave is based solely on the medium that it's in. So if I increase that tension again, you can see it gets faster and faster. Notice how the wavelength is changing because my frequency is fixed. And if we brought up the equation sheet, you would see that there is a straightforward relationship between the two of them. So let's bring up that equation. All right, so here's our equation sheet. You can see the velocity is related to the wavelength and the frequency. It is not determined by the wavelength and frequency. The velocity is determined by the medium, and then the wavelength and the frequency have this inverse relationship. When multiplied together, they equal the velocity, but they do not determine the velocity. That is a really big point. All right, so that's it, and I will see you in class.